Although Lewis's approach to chemical bonding helps us to write the structure of molecules, it suffers from certain drawbacks. These drawbacks are: it fails to explain the formation of a chemical bond. It does not give the reason for the difference in bond dissociation energy and bond lengths in molecules like hydrogen and fluorine, although in both the cases a single covalent bond is formed. It also fails to give any idea about the shapes of the polyatomic molecules. The VSEPR theory, on the other hand, gives the geometry of the simple molecules but fails to explain their formation. To overcome these limitations, the valence bond theory and the molecular orbital theory, which are based on quantum mechanics, are introduced. The valence bond theory was introduced by Heitler and London and was developed further by Pauling and Slater. It explains the formation of covalent bonds. According to this theory, a covalent bond is formed when a pure valence atomic orbital of one atom overlaps with pure valence atomic orbital of another atom. Each of the overlapping orbitals contains the unpaired electron of opposite spin. The electron pair is shared by both the atoms. The strongest bond is formed when the orbitals of the two atoms overlap to the maximum extent. Let's explain the formation of hydrogen molecule on the basis of this theory. Consider two hydrogen atoms, A and B, approaching each other. Let us label their nuclei as Na and Nb and the electrons present in them as Ea and Eb. Now, as these two atoms come closer, forces of attraction as well as repulsion begin to operate. The force of attraction arises between the nucleus of one atom and its own electron, that is, between Na and Ea, and between Nb and Eb, and the nucleus of one atom and electron of another atom, that is, between Na and Eb, and between Nb and Ea. Simultaneously, repulsive forces also arise between the two electrons Ea and Eb, and the two nuclei Na and Nb. Experimentally, it is found that the magnitude of the new attractive forces is more than that of the new repulsive forces. As a result, the potential energy decreases as the two hydrogen atoms approach each other. Ultimately, a stage is reached where the nuclei remains at an optimum distance, such that the net force of attraction balances the net force of repulsion. At this stage, the system acquires minimum energy, and the two hydrogen atoms are said to be bonded to form a stable molecule. If we try to bring these atoms still closer, then the repulsive forces start overpowering the attractive forces. Consequently, energy of the system increases, causing instability to the system. As energy is released during the formation of the bond between the two hydrogen atoms, we can say that the hydrogen molecule is more stable than the isolated two hydrogen atoms. The energy so released is called the bond enthalpy, which corresponds to the minimum as shown in the figure. It is important to note that the same amount of energy is required to dissociate one mole of hydrogen molecule. Another example is the formation of a hydrogen chloride molecule. Here, when hydrogen atom approaches chlorine atom, a bond is formed due to the overlapping of s and p orbitals. The overlap can be positive, negative, or zero depending on the properties of the respective overlapping orbitals. Based on the overlapping of orbitals, two types of covalent bonds are formed. These are known as sigma and pi bonds. Sigma bonds are formed by the end-to-end overlap of atomic orbitals along the internuclear axis, known as a head-on or axial overlap. There are three types of head-on overlaps that form sigma bonds. They are SS overlap, SP overlap, and PP overlap. SS overlapping takes place when two half-filled s orbitals overlap along the internuclear axis. SP overlapping takes place when the half-filled s orbital of one atom overlapped with the half-filled p orbital of another atom along the internuclear axis. PP overlapping takes place between two half-filled p orbitals of two atoms along the internuclear axis. A pi bond is formed when atomic orbitals overlap in such a way that their axes remain parallel to each other and perpendicular to the internuclear axis. The pi orbitals formed due to the sidewise overlap consists of two saucer-type charged clouds above and below the plane of the participating atoms. Pi bonds can be formed in addition to a sigma bond between two atoms and are always present in molecules with multiple bonds. The overlapping of orbitals extends to a larger area in sigma bonds than pi bonds. Therefore, sigma bonds are stronger than pi bonds. The overlap criterion of orbitals applies equally to both diatomic molecules and polyatomic molecules. However, the valence bond theory fails to determine the actual shapes of the polyatomic molecules, such as methane, ammonia, and water, which are tetrahedral, pyramidal, and bent respectively. Let us explain the above limitation by considering methane molecule. In methane, the central atom carbon has the configuration of 1s2, 2s2, 2px1, 2py1. In its excited state, the configuration becomes 1s2, 2s1, 2px1, 2py1, 2pz1. The four atomic orbitals of carbon, each with an unpaired electron, overlaps with four singly occupied 1s orbitals of the hydrogen atoms to form four CH bonds. We know that p orbitals lie perpendicular to each other. Hence, the three CH bonds in methane molecule are expected to be oriented at 90 degrees to one another. The two s and 1s orbitals of carbon and hydrogen can overlap in any direction, since they are spherically symmetrical. Thus, the direction of the fourth bond cannot be ascertained. This means that all the four CH bonds in methane are not identical. But experimentally it is observed that all the four bonds are exactly identical in all aspects and are oriented at a bond angle of 109.5 degrees. Similarly, valence bond theory cannot account for the correct bond angles in water and ammonia. While valence bond theory predicts to have a bond angle of 90 degrees in them, the experimental result suggests to have bond angles of 104.5 degrees and 107 degrees respectively. Thus, it can be seen that the valence bond theory fails to account for the actual shape of polyatomic molecules. During their research, scientists observed that some molecular structures found in nature could not be scientifically explained with the help of the existing understanding of atomic orbitals. Pauling introduced the concept of the hybridization of atomic orbitals to explain the existence of such molecules. During hybridization, atomic orbitals of slightly differing energies redistribute to form a new set of orbitals with equivalent energies. The number of hybridized orbitals formed is equal to the number of atomic orbitals participating in the process. These hybrid orbitals align themselves in space such that there is minimum repulsion between the electron pairs. Because of this, the bonds formed by hybrid orbitals are more stable as compared to those formed by pure atomic orbitals. The phenomenon of hybridization is observed in the atomic orbitals s, p and d. Their possible combinations are sp, sp2, sp3, sp3d and sp3d2. Now let's study each combination in detail. In sp hybridization, one s orbital combines with one p orbital to form two equivalent sp hybrid orbitals. The hybrid sp orbital shows 50% characteristics of the s orbital and 50% characteristics of the p orbital. The hybrid orbital has a large positive lobe and a very small negative lobe. The hybrid orbitals are oriented in opposite directions, forming an angle of 180 degrees with each other. During bond formation, they provide maximum overlapping areas, making the bonds stronger and giving the molecule its linear structure. Some compounds whose central atom displays sp hybridization are BeCl2 and C2H2. In sp2 hybridization, one s orbital combines with two p orbitals to form three equivalent sp2 hybrid orbitals. They have a trigonal planar arrangement, and the angle between two orbitals is 120 degrees. Some compounds whose central atom displays sp2 hybridization are BeCl3 and C2H4. In sp3 hybridization, one s orbital combines with all the three p orbitals to form four equivalent sp3 hybrid orbitals. Each hybrid sp3 orbital displays 25% s orbital characteristics and 75% p orbital characteristics. They have a tetrahedral arrangement, and the angle between two orbitals is 109.5 degrees. Some compounds whose central atom displays sp3 hybridization are CH4 and C2H6. The hybridization of elements containing d orbitals leads to three distinct hybridized shapes formed by the mixing of s, p and d orbitals. They are dsp2, sp3d and sp3d2. Of these, we will study sp3d and sp3d2 hybrid orbitals closely. The energy of 3d orbitals is not only comparable to 3s and 3p, but also comparable to 4s and 4p. Therefore, the hybridization of d orbitals either involves the 3s, 3p and 3d orbitals, or the 3d, 4s and 4p orbitals. In sp3d hybridization, one s orbital, 3 p orbitals and 1 d orbital combine to form 5 sp3d hybrid orbitals of equivalent energy. They have a trigonal bipyramidal arrangement, which leads to the formation of two different sets of angles between orbitals. 3 of the hybrid orbitals lie in one plane, making an angle of 120 degrees with each other. This plane is called the equatorial plane, and the bonds formed by them are called equatorial bonds. The remaining two orbitals arrange themselves above and below the equatorial plane, forming an angle of 90 degrees with the orbitals on the equatorial plane. The bonds formed by these two orbitals are called axial bonds. The axial bonds are repulsed by the equatorial bonds, causing them to be longer and weaker than the equatorial bonds. Ultimately, this makes molecules with sp3d hybridization more reactive. The central atom, phosphorus, in the compound PCl5 displays sp3d hybridization. In sp3d2 hybridization, one s orbital, 3 p orbitals and 2 d orbitals combine to form 6 sp3d2 hybrid orbitals of equivalent energy. They have an octahedral arrangement and a bond angle of 90 degrees between the orbitals. The central atom, sulfur, in the compound SF6 displays sp3d2 hybridization. Thus, we can observe that the phenomenon of hybridization explains the characteristic geometrical shapes of polyatomic molecules.